Yes, welcome back. You can hear me now, right? Yeah. Yes. Okay. Thank you. Thank you very much. And I'm really sorry for the inconvenience. There is some problem with the mouse on this on this laptop. Anyway, it's fixed now. Yeah. Before we start, do we have any questions from what we discussed in the previous session? Okay. How was the exam? What's the how did the exam go? Okay. Did it feel all right, or is there anything that you feel we have not quite covered in the class? Okay. When I worked on the questions, yeah, thank you. When I worked on the questions, I ensured that uh, we uh, we have questions only based on what we discussed in class and only what we have in the slides. Okay, so we'll do the same thing for the final exam as well. Okay, note that final would be a comprehensive exam, but then there will be a split as to we'll have about two-thirds, approximately two-thirds for two-thirds of the questions or two-thirds of the points focused on what we discussed after the midterm, okay, which would be memory management and all the other topics after that. Okay? And 30% would be from the previous topics. Okay? So that's what I'm planning, okay, for the final exam, and that should be it. The exam is already graded, so we should have them either Thursday or Friday. They should be released by Friday. Okay. So that's regarding the exam, and let's get back to what we were discussing in the previous session, which is memory management. Okay. So oh yeah. So as part of this particular module, we were talking about how the memory module uh, is how the overall available physical memory is managed across different processes. Okay? How the processes would have their would have their code and data available in physical memory so that they can be uh, so that uh, so that the instructions and data can be accessed by the processor. So that's approximately what we were talking about, and main memory um, uh, and in this particular module we'll also talk about the how the operating system would ensure this protection boundary, okay, in spite of having multiple processes loaded into memory at the same time. We had a brief talk regarding the physical regarding various components of the operating system and how they relate to the memory management module. Okay, and yeah, we talked about the process address space, as well as one important aspect that we talked about is address binding. Okay, and as we discussed, address binding can be done at three different times uh, with respect to the execution of a program. Okay, one is it is usually done at um, one option is to do it at the load time when we have this relocatable object code available on some persistent storage, and when it is time to uh, execute, when it is time to execute, or when we have sufficient, when we have the required amount of physical memory available, so that the process can be loaded loaded into physical memory. At that time, naturally, we will know exactly at what starting from which memory location the process is going to be loaded. Okay? So at that time, we should be able to convert the relocatable addresses from to the actual physical addresses, okay, or the absolute addresses in physical memory. So that is uh, so um, um, so that is how we can perform the address binding at the load time. Otherwise, if we already have the required otherwise if somehow we know a priori if the actual memory locations where the program is going to be loaded, program and data um, are going to be available, then what we can do is we should be able to provide those addresses at compile time itself, and we should be able to um, perform the binding at compile time, or in other words, we should be able to convert the relocatable addresses to the actual physical addresses or our absolute addresses during compile time itself. Okay, and one advantage of one advantage of performing address binding at compile time or load time is that we is that there is no uh, performance penalty as perceived by the user at runtime, because the instructions uh, already have the physical addresses available. Okay, so but one limitation with these two approaches, the compile time binding at compile time or the load time, would be that we need to know the exact physical addresses beforehand, and if there is a need, for whatever reason, if there is a need to move the process the process address space from one physical memory location to another physical memory location, then either we need to reload. If we have performed the binding at the load time, we need to reload the entire address space of a particular process, or if the binding has been done at compile time, then we may also need to recompile before we can move it to some other identified memory location. Okay, so that is a limitation with these two approaches. Okay, and for that reason, usually it is not used, even though it results in better performance, okay, or faster execution of the program. Okay. And third option of address binding is performing the binding at execution time or at runtime, where whenever a process sees a relocatable address as part of the instruction, uh, what it does is it passes that information to the memory management unit, and that will perform the conversion, and then accesses the corresponding physical memory location and fetches the appropriate fetches the data element which is available at that location. Okay, so that the instruction execution can continue. So we are practically delaying the conversion of relocatable address to the actual physical address until until each specific instruction is executed. Okay, and considering we are performing at the execution time, naturally we need hardware support, and we have the memory management unit which performs this conversion. Okay? And one advantage with this particular approach is we should be able to move the we should be able to move the uh, process address space to any physical memory location, and 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 still we should be able to execute the program. So that is one advantage with this particular approach. Um, so we have looked at how the logical address is converted to the logical or relocatable address is converted to the physical address. Okay. As I mentioned, memory management unit is the one which is responsible to perform that task, and here we have one simple solution where we where as part of the uh, where we where we can specify the memory location, where the starting memory location of the process address space, okay, um, in physical memory, and that address will be stored in a special register, which is a pre-location register, and the memory management unit will make use of that address to convert the logical address to the physical address. Okay? And this is one example that we have seen. And here we have some concepts uh, to have a quick understanding before we get into a little more detail. One of them is dynamic loading, where if we have if we have any where if we have the where if the process has multiple routines for all the special cases which are not usually used, then we should be able to use this dynamic loading feature and ensure that only the routines that are required are loaded into physical memory, and not all the possible and not the entire program, which considers all possible cases. Okay. So and thereby we should be able to make better physical memory utilization, um, because uh, uh, because uh, because we may be able to load multiple processes, considering for each process we are only loading only the required components or required routines. Okay? So if there are any infrequently occurring cases and we are not using it, then we do not need to load them into physical memory. Okay? So that is the concept of dynamic loading, and dynamic linking is a concept where rather than linking all libraries as part of the uh, code, as part of the object code, what we can do is we should be able to we should be able to place the uh, place the library routines in a different part of the physical memory, and as part of each process which um, which includes which includes these which includes these libraries, what we can do is we should be able to simply have a stub instead of the entire library routine. And whenever the stub is referenced or called, what we can what this one does is um, the stub will be replaced with the actual physical memory address where the library routine is placed. Okay? So there are a couple advantages here. If that so Um, so one advantage with this particular approach is if there are multiple processes loaded into memory which are accessing the same libraries or same library routines, then we should be able to using this particular feature we should be able to access the same library routine or same part of the memory um, from multiple processes. Okay, so but especially for this one, we need support from the operating system because, as I said, um, each process each process is allocated one address space, and it is the job of the operating system. It is one of the responsibilities of the operating system to ensure that not all processes are to ensure that a process cannot access the address space or the set of memory locations which are allocated to some other process. Okay? Now, in this particular case, if we have a library routine loaded into physical memory, and if we want multiple processes to simultaneously access those set of memory locations where this particular library routine is placed, then um, then operating system needs to provide that additional support to attach that attach those memory locations as well to the physical address space of each of these multiple processes. Okay. So for that reason, we need support from the operating system for this. Okay. And one other advantage with this dynamic linking approach is we should be able to independently change the library routines at any point in time. We should be able to patch them and fix them, and we can also maintain multiple versions of these library routines, and and we can we can have we can have we can have the version information along with as part of the stub itself, so that it can access uh, it can access a specific version of the library routine. Okay, um, so that is another advantage of this particular approach. Okay, so that's another concept. Uh, so before we move further, we have one other concept that we need to be aware of, okay, to better understand the various ways in which memory can be managed, okay, which is swapping. Okay. If you remember, when we were talking about process management, we discussed that each process will be in multiple states, right? At any point in time, it is in a specific state. Either it is ready and either it is ready to be executed and running, right? Either it is ready to be executed and waiting in the ready queue, or or it can be running, okay, or a particular process can be waiting for some pending IO, right? Um, or uh, and all these three different stages that I mentioned are valid for all the processes which are loaded in physical memory, right? And there may be a situation where a particular process is ready to be executed, but it is not allocated the physical memory space yet, and for that reason, it continues to stay on the persistent storage, okay, which has more storage capacity, as we have seen earlier. Okay, so what happens is at um, uh, when at specific at specific points in time, we have this long-term scheduler in the system, which will make a decision to move one of the processes from the persistent storage to the ready queue. Okay? To the ready queue, so that it can be executed at some points in time. Okay? And then once we have multiple processes in the ready queue, it is the job of the short-term scheduler to make a decision as to which one of those ready processes can be allocated the processor, can be scheduled for execution. So so here we are really talking about the job of the long-term scheduler, which um, which has which selects a particular process which is already available, which is ready to be executed, but available on the persistent storage. Okay? And and if there are any, and we have also looked at one situation, we have also discussed at one situation where we have multiple processes which are already loaded in physical memory, but there are several of them which are waiting for some event to occur, or in other words, we have these several processes waiting in all these different wait queues, and the ready queue does not have sufficient processes to keep the processor busy enough. Okay, if that is the case, again it is the job of the long-term scheduler to select one of the processes from the persistent store which is ready to be executed and move it into the ready queue. Right? So, but um, as the long-term scheduler makes a decision to move one of the process into the ready queue, uh, um, prior to that, it needs to move the process from the persistent store to the physical memory. Yeah, or in other words, it needs to allocate some physical memory space to the incoming process, okay, from the backing store, the persistent store. Okay? And if that is the case, and if we do not have sufficient space in the physical memory, and if we have any one of the process which is simply waiting, for example, uh, which is waiting as part of some wait queue, okay? If that is the case, then that particular process will be swapped out, placed onto the backing store, and another selected process will be swapped in. Okay? So in this particular case, we have process P1, which is already in physical memory, but it cannot be executed because it is part of some wait queue. Okay? And if that is the case, then we should be able to swap out process P1, and we should be able to, or the long-term scheduler should be able to swap in the process P2 into the physical memory. So so this particular procedure is referred to as process swapping. Okay? As in, we are trying to move a process back and forth between physical memory and the persistent storage. Okay? Okay. So in this particular manner, we can have we should be able to have more rather than simply making use of only the physical memory space to have the processes ready for execution. We should be able to leverage the capacity, the storage capacity that we have on the persistent store as well, to have more number of processes active in the system by using this swapping approach, okay, swapping method. Okay, so for that reason, the overall physical memory space of the processes which are active in the system, it can exceed the actual physical memory which is available. Okay, but so that is one of the advantage with using this swapping. But as it is obvious, one limitation is that whenever we want to schedule a new process, there may be a situation where there is a where we do not have where there is a need to actually fetch a process from the persistent store, and if that is the case, then we will have this overhead of swapping out a process and before swapping in the required process, and all this would contribute to the context switch time. Okay? So that is an overhead with this particular approach. Okay? So the overall transfer time, the swap in and swap out time, that will have an impact on the context switch, on the overall context switch time. Okay? So that's one thing that we have to one thing that we have to remember. Okay? And so to make use of this particular approach, there are some factors that we need to consider. Okay? One thing is we to make use of this particular approach, we must know how the address binding is performed for each of these processes. Okay? Or in other words, specifically, we want to know if the address binding is performed at execution to be at execution time, or was it done at load time or compile time. Okay? Again. if we know for sure that a swapped out process will be swapped back in at exactly the same set of memory locations as it was residing earlier prior to swap out, then the particular process will not see any impact, irrespective of whether the uh, irrespective of whether the binding was done at compile time or load time or execution time. Okay? Because there is no change in the addresses itself, right? So it does not really matter. But if the particular process cannot be loaded at exactly the same set of memory locations, then if the process has been if the process has the address binding done at compile time or load time, then then the addresses would change for different components, right? For different elements, and for that reason, uh, the process need to be recompiled or reloaded, and for that reason, this particular approach of swapping out to a persistent store and swapping back in at later point in time, it does not work. Okay, so this particular approach, it can be applied only to the processes which can have the address binding performed at execution time. Yeah, so that is an important aspect that we need to consider. Okay. Another aspect is, as I mentioned earlier, uh, some of these processes are swapped out because the process is waiting for some reason. Okay? And if the process is in fact on the wait queue for some IO, or yeah, or if there is any pending IO that is that is or that is there for that particular process, then again that is a special aspect. That is an aspect that we uh, need to consider. Okay, uh, so let's say if this process P1 is waiting for some IO, or if it is waiting for a response from one of the IO devices, for example, okay? And if it moves, if it is swapped out, and let's say another process P2 is arrives or is um, placed at the same memory locations, then at that point in time, if that if there is a response received from the IO device, that that may impact that may impact the data that belongs to a different process now. If that IO is, let's say, is written to the prior given address, okay, that prior given address is, it now belongs to process P2 and not process P1. Okay, so that may lead to corruption of the address space of a particular process. Okay, so that is a problem. Okay, so if there is any pending IO, then we need to take some special care. Okay, one particular solution to that problem is, if any process is in fact waiting for an IO, then we do not swap out that process uh, at all until the IO is received. Yes, so that is one solution. Another solution would be to um, ensure that um, all the IO that is sent or received uh, from any of the IO devices is not written directly to the address space of a particular process. Instead, it is written to some location as part of the kernel address space. Okay? And at some point in time, when the operating system is aware that the corresponding process is loaded in physical memory, it should be able to make a second transfer from the kernel address space to the process address space. Okay? So that will ensure that that IO is always written to the appropriate process. Okay, so that is a second solution. But with the second solution, as we can clearly see, we have this IO device that is writing to the kernel address space, and then there is a second copy that is being done to the process address space instead of IO device directly writing to the process address space. Right? So that is an overhead again. So those are some additional aspects that we need to consider with this particular approach. Okay? And note that here we are really talking about swapping out entire process address space and then swapping in entire address space of some process. Okay? And clearly we can see that copying entire address space is a huge task, and that will be a lot of effort, and that takes a lot of time as well. It consumes lots of resources and time. Okay? And for that reason, swapping is it's usually disabled. This particular approach in this particular form is not directly used in modern operating systems. Okay? And even in situations, in some special situations when this approach is used, especially in situations where there is insufficient physical memory space available, usually the operating system would start swapping out some of the processes from physical memory to the persistent store, but it will stop the moment the moment there is sufficient free memory available in the system. Okay? So yeah, so these are some aspects that we need to remember here. Okay? Do we have any questions on this topic? Okay. Yeah, something simple, but this is one of the basic topics. We'll see that, as I said, this particular approach is not normally used in modern operating systems, but a different variation of it is being used in the modern systems. Okay? So this is more of an introduction to this concept. Okay? And as I said here, swapping in and swapping out, it leads to it leads to a lot of overhead, right? As in, it has a impact on the overall context switch time of processes. So here we have one example, which from which we can understand how big is the impact. Let's say we assign about 100 megabytes of physical memory to a particular process, and if we want to swap out that process, which is allocated about 100 MB space, to the hard disk, or which is the persistent data store, and let's say the disk has this transfer rate of 50 megabytes per second. If that is the case, it will take about 2 seconds, right, to swap out an entire process. Okay? Now that we have a free memory capacity available, we may want to make use of it by swapping in one of the ready processes from the persistent store. And let's say we have another process which is about the same size, 100 MB, and let's say we want to swap in that process, which will take again another 2 seconds. Right? So the overall transfer time for swap out plus swap in would be 4 seconds. Right? So it will be, so all this amount of time will be added to the to the context switch time if this process is done, if the swap out or swap in is done during the as part of the context switch. Okay? So so this is the kind of overhead in terms of time that I was talking about. Okay? And note that here we are really talking about swapping in or swapping out the entire address space of a particular process. Okay? When I talk about the address space, it is the actual physical memory locations which are allocated to a particular process. But then it is not normally the case that the entire address space is being utilized by the process. Okay. Uh, so uh, so if that is the case, or and if there is a way for us to know exactly what part of the uh, address space, physical address space, that is actually being utilized by the process, then we should be able to then we should be able to copy or swap in or swap out only those memory locations which are actually being utilized. Right? So that is one way we can improve the performance or reduce the amount of swap in swap out time. Okay? Um, so so here, if there is a way that the operating system can be made aware of exactly what parts of the memory, what parts of the allocated physical memory is being utilized by the process, then it can make better decision regarding the swap in and swap out. Right? So, so for that reason, if we can, if the process can make the operating system aware of the exact memory locations by which are being utilized, by ensuring that um, all the allocations and all the release is requested only through system calls. Whenever we perform a system call, the system call goes through the it is um, it goes through the kernel, right? So operating system is aware of what task is being performed, and and as part of that, so if there is a way that the process can perform all the allocations and deallocations only by using system calls, then operating system can be made aware of the actual memory locations which are in use at any given point in time. Okay, if that is the case, then we should be able to, then it can make a better decision and thereby reduce the total swap in swap out time. Okay? So that is one tweak over there, but as it is obvious, it may not always be the case. Okay? It is difficult to ensure that the operating system is involved all the times. Okay? So that is just one concept. Okay? Now let's excuse me. So now let's get back to our concept of memory management. As we discussed the other concepts, as we discuss various approaches to see how the actual physical memory is managed, or the managed among these multiple processes which are which reside in the physical memory, we see that whatever concepts that we have discussed so far, we see how they come into play. Okay. So do we have any questions here before we continue? Okay. Okay. So let's just continue with the rest of the topic. Okay. So we have discussed earlier that that we to perform the address binding at um, uh, at runtime or at execution time, we have the memory management unit which performs the relocation and which converts the logical addresses to the corresponding physical addresses. Okay? And in this particular case, we are assuming that we have the process loaded in loaded from starting from one address which we have placed in the relocation register. Okay? We say that a particular process is starting from a given address, and the entire address space of a particular process is located in contiguous memory locations starting from that address. Okay? or in other words, we are just saying that the entire process is loaded in the same part of memory, okay? in adjacent or in consecutive memory locations. So so that is the contiguous allocation approach, okay? That's the basic one that we have discussed earlier. So so as we can see here, we have this entire physical memory, right? So we have this entire physical memory in which we have one or more processes loaded into the physical memory, okay? And it's not just the processes that are allocated physical memory, but we also have some part of the memory allocated to the operating system, right, to store some kernel data structures or any additional pieces of information that is required to manage the resources in the entire system by the operating system, okay? So we have some part allocated to the operating system, and we have the entire remaining part available to place these to be allocated to various processes, okay? So now to be sure, we have one end of the operating system allocate one end of the physical memory allocated to the operating system, and the other end is allocated to the processes, okay? And of this entire space available, each active process in the system is loaded into some part of the physical memory, um, some part of the physical memory. And as part of this approach, the contiguous allocation, each process is allocated only one chunk of the physical memory, which with contiguous addresses, okay? So the entire address space of the memory is located in one part of the memory, okay? So okay, and whenever the address binding is performed, um, the operating system should be able to, as part of the memory management unit, it should be able to ensure that all the references are being made by the process only to valid locations. Or in other words, if a process is allocated addresses from say 1000 to 2000, okay? um, allocated physical memory from address 1000 to address 2000, okay? If that is the case, then um, it should be able to verify here as using the limit register. It should be able to verify and ensure that all the addresses are valid addresses that are being referenced, okay? Yeah, using the relocation register as well as the uh, base and limit registers, it should be able to, the operating system should be able to verify and ensure that all the references that are being made in the process are in fact to the actual physical memory locations which are part of the address space of that process, okay? And only if that is the case, the memory management unit will fetch the data from that particular location. Otherwise this any if referenced is made to some any other address which is outside the allocated uh, block of addresses, then there will be a trap that gets generated, okay? So so this is kind of this is one form of hardware support that we have available to perform this check, okay? As part of this contiguous allocation approach, okay? So that's in brief regarding that particular approach, okay? Now here we were talking about each process. We were talking about having this physical memory allocated to multiple processes, right? And again, it is a considering memory is a limited resource, and especially so the case with the physical memory, we or the operating system must ensure that the memory is allocated in an efficient manner to multiple processes. Okay. So, so for that reason, we have a couple of approaches. Okay. So first one is static memory partitioning, or in other words, what we can do is we can partition partition the entire available physical memory space into some number of partitions, uh, partitions uh, with some number of partitions having some predefined capacity, predefined size. Okay? And whenever there is a request from some of the process, whenever there is a request from some process for some amount of, whenever there is a request from some process uh, of some size, what we can do is of all the available partitions in the physical memory, we should be able to find an appropriate one, and then we should be able to load the process in that selected partition. Okay, so that's the concept of static memory partitioning. Okay, and considering we're talking about partitioning the memory beforehand and then identifying which of those available partitions is an appropriate choice for an arriving or incoming process, uh, we should be able to partition the memory in two different ways. One, we can have all the partitions to be of same size, or we can, if we know what kind of processes will be executed on this system, then we should be able to pre-partition based on those expected process sizes. As you can see here, we have partitions of different sizes, and here we have partitions of equal sizes. Okay? And this is this seemed to be a more um, this seemed to be an easier problem to allocate a particular to allocate a partition to an arriving process, because all the partitions in this particular case are of equal size. So any available, so any free partition can be allocated to the arriving process. But with this particular approach, one difficulty is to to uh, to find or to come up with a partition size itself, a size that would be sufficient to most or nearly all the processes that need to be executed on the operating system. Okay? So that is a difficulty with this particular approach. Okay? Whereas with the and one of the limitations with this particular approach is whenever we load a process, there may be a situation that uh, there may be a situation that the process may not need the entire partition space, and thereby it may have been allocated more memory capacity than is required. Okay? And if that is the case, there is at least some memory capacity which is allocated to the process which it does not need, and thereby it will get wasted. Okay, that's one of the limitation with this particular approach, and that kind of wastage of memory area that can be reduced by making a more appropriate choice among partitions among partitions which are of different sizes. Okay? With this second approach here. Okay? So, but then it is not always the case that we can predict the sizes of all the processes beforehand. And for that reason, even with this one, we can have some memory capacity that is wasted. Okay, so yeah, Now, one important thing to note here is if you see here, we have this entire physical memory. This is the entire physical memory capacity that is available, and we are aware that only one process can be loaded into each of these partitions. So at any point in time, it's only these many number of processes uh, equal to the number of partitions that we can have active in the system, or in other words, the number of partitions that we make in the physical memory that defines the degree of multi-programming. Okay? Because it's only those many number of processes that can be active in the system, that can be loaded and active in the system at any point in time. Okay, so it's because it is being done statically, okay, and not during runtime. It is a it is a big decision to make as to what would be the number of partitions and how the and what would be the sizes of different partitions. Okay? And that needs to be done before the during the system setup time. Okay? And okay. So all these are different aspects to consider with this particular approach, the static memory partitioning approach. Okay. Do we have any questions here? Okay. Clearly, this is clearly there is less freedom here, and this kind of memory management technique is its capability is too limited, right? And it is difficult to adopt this approach, this memory management approach to the modern operating systems where we have different kinds of processes, and we do not want to we do not want to um, we do not want to have a prior view or predict exactly what kind of process will be executed on the system. Okay? So for that reason, this particular approach is one of the earliest approaches that were developed for memory management, and it is not being used in modern operating systems yet. Okay, but then we want to understand how this particular approach works, so that we can see what are the drawbacks and how do we improve the system, okay, to overcome those limitations. Okay, so yeah, so here we have some limitations with the static memory partitioning approach. Okay. First one is there, as we have seen earlier, there may be it may be difficult to it may not be optimal to uh, to to uh, to design partitions such that a given partition would fit the maximum possible uh, size of an arriving process. So if that is the case, let's say in this particular case we have a huge large partition created here, and and if we have and if we allocate such a partition to any other process which is smaller than this this partition, then there will be a huge amount of memory capacity that will be allocated and is not being utilized, or in other words, that memory capacity is currently being wasted, okay, because it cannot be allocated to some other process. Okay, so for that reason, if we select smaller partitions so that we can have a higher degree of multi-programming, there may be a situation where we may have larger processes which cannot fit in to any of the partitions which are available. Okay? And if that is the case, what we do is we use this concept of overlays, where we load only part of the process into a partition, and if the as part of execution, if the process needs the part of the address space which is not loaded in physical memory, what it does is it swaps out a small part of that loaded uh, address space. It swaps out and then swaps in the required set of locations, okay, required part of the process address space. Okay. So that concept is referred to as overlays. Okay, so if a program is too big to fit into a partition, only a part of the process uh, process address space will be loaded into the physical into the partition, and it will make use of this concept of overlays to swap in and swap out the required part of the process. Okay, so that is again that will again lead to runtime overhead, okay, and delays at runtime. Okay, so that's of course one of the limitations here, that we cannot fit in processes which are too big for a given partition. Okay, and of course, if we have any small processes which are allocated a partition of larger size, then there may be some memory capacity which is allocated and not being utilized. Okay? So it is so if there are any small processes, they may not efficiently utilize whatever partition space that is allocated. Okay? And thereby the overall memory utilization is not quite efficient, okay? Because there is some memory that is being that is utilized and that is allocated but not being utilized. Okay? And this and that kind of memory capacity which is allocated to a specific process but is not being utilized by the process itself, that is referred to as internal fragmentation. Okay? That's referred to as internal fragmentation, and this leads to low utilization of memory capacity. Okay? And as I said, the number of partitions, the system needs to identify the exact number of partitions and the sizes of the partitions beforehand during the system setup time, and the degree of multi-programming, it depends on the number of predefined partitions, because we can have only those many number of active processes in the system, okay? One process per partition. So so we cannot dynamically change the degree of multi-programming depending on what kind of processes are being executed and what kind of and what are their process needs. So those are all the different limitations with this static memory partitioning approach. Okay? And as I mentioned earlier, this is one of the earliest memory management techniques that were developed to partition the available memory and allocate it to multiple active processes. Okay? And considering all these considering all these limitations from static approach, we do not use this approach as is in any of the modern operating systems. Okay? Instead, we will see how this approach is tweaked and is considered so that and is adapted for modern operating systems, so that we can overcome at least some of these limitations. Okay, do we have any questions here? Okay, so far we were talking about a static memory partitioning approach, or in other words, we know exactly how many partitions that we are going to make and of what sizes given a memory module. So and instead of statically predefining the partitions, what we can do is we should be able to do it dynamically or at runtime. Okay? So what we in this particular approach, in this dynamic memory partitioning approach, what we can do is we should be able to consider the entire available memory capacity, entire free memory capacity, as one single whole, okay? As a big chunk of memory that is available. Okay? And as requests arrive, what we do is we go ahead and allocate those, allocate a part of, we can create a partition and allocate that, um, allocate the required amount of capacity to the arriving process. Okay? So, so the partitions are actually made upon request by the arriving process. Okay? So uh, the allocated an arriving process is allocated memory from a whole, which, or in other words, the free memory capacity. Okay? And whenever a particular process uh, completes its execution or it leaves the system, what it does is it simply frees that partition. Okay? And if we have adjacent free partitions, then they can be combined rather than strictly defining the partition, rather than strictly defining the partition boundaries. What we do is if we have adjacent free partitions, we simply combine it and consider it as a free memory capacity to be allocated to any of the arriving future uh, process. Okay. So for that reason, as even though we start the system as having one one whole or one chunk of memory with which can be allocated, as processes arrive and leaves the system, there may be multiple holes that get generated. Okay? So at some point in time during the execution, it would look something like this. So in this particular case, we have three processes where we have process 2, process 5, and process 8, which are loaded into memory in this particular form. At some point in time, process 8 leaves, leaving a big hole here, as you can see. Okay? And at some point in time, let's say process 9 requests this amount of space, which is allocated. And at some point in time, let's say process 5 leaves the system, then we have two different holes like this. And we have two different two process 2 and process 9 loaded in memory. Okay? So and again, it's the job of the operating system to maintain information regarding all these allocated and free processes. Okay, free partitions, or in other words, what part of the um, what part of the memory is free to be allocated, and at what locations are different processes are loaded at this current point in time. Okay, so with this particular approach, one advantage is uh, if there is an appropriate um, sized hole available which can serve the needs of a given process, then we should be able to allocate it, as you can see here. Whereas that is not really the case with the static memory partitioning approach. For example, if we have this kind of partitioning approach where let's say there is a request for um, allocation by a process for about let's say 12 MB. Okay, even if we have two different partitions which are adjacent and are free, we cannot really allocate um, two partitions using this particular approach. Okay, whereas that is not really the case here with dynamic memory partitioning approach, because we are coalescing the adjacent holes. Yeah, or in other words, we are combining the adjacent holes, and we consider it as a single whole. Okay, so so in that particular manner, we should be able to cater to the needs of any large processes, and if there is a and even though if we have a large hole like this, if the process needs only a small part of it and not the entire partition, then we should be able to allocate only the requested amount of space. And thereby, if you see here, we are not, we have the remaining space available for any newly arriving processes. Okay, so and thereby we should be able to make better use of the available physical memory. Okay, so those are all different advantages with this particular approach. Okay, do we have any questions here? Okay, so we'll continue this topic in the next session. Okay, okay, thank you. You all have a good day.